Our Sun is not simply floating in the Milky Way. It is buried inside a specific structure, one that most people have never thought about, and one that is so enormous that even the word enormous fails to do it justice. The structure is called the Orion Arm, and right now, this instant, you are inside it. Every star you have ever seen with your naked eyes burns somewhere within its boundaries. Every constellation humanity has traced across thousands of years of history lives within its volume. Every telescope pointed at the night sky is looking through its gas and dust. And yet almost no one knows it exists, and almost no one can feel it. That invisibility is not accidental. It is the direct consequence of scale. Light, the fastest thing in the physical universe, needs 20,000 years to travel from one end of the Orion Arm to the other. 20,000 years. Agriculture began roughly 10,000 years ago. Recorded human history spans less than 6,000 years. The light that left the far end of the Orion Arm before any of that began, before any human writing existed, before any city had been built, is still traveling toward us right now, and will keep traveling for another 10,000 years before it arrives. That is the structure you live inside, not the galaxy, not a galaxy cluster, just the local arm. Between your front door and the full sweep of the Milky Way sits an intermediate structure, a galactic feature with defined edges, a measurable width, a traceable length, and an internal anatomy complex enough that scientists spent the better part of a century arguing about whether it deserved to be taken seriously. For decades, maps of the Milky Way labeled it a minor spur, a small offshoot connecting more impressive arms, the galactic equivalent of a dirt road between two highways. That classification turned out to be wrong. Not slightly wrong, significantly embarrassingly wrong. And the story of how astronomers discovered the truth is as striking as the truth itself. The Milky Way is a barred spiral galaxy. If you could somehow hover 100,000 light years directly above it and look down, you would see a flattened disk of stars, gas, and dust organized into sweeping curved arms emerging from either end of a central elongated bar. The galaxy spans roughly 100,000 light years from edge to edge, possibly more depending on how you define its faint outer fringe. It rotates. It has architecture, and within that architecture, the material is not spread evenly. Stars and gas concentrate along the arms, compressed there by the gravitational dynamics of the spiral structure itself, piling up in dense rivers of stellar activity that trace the Milky Way's most distinctive visual feature. The galaxy has two confirmed major spiral arms. The Perseus arm lies farther from the galactic center than our position. The Scutum Centaurus arm wraps around closer to the core, and both of them are enormous, stretching tens of thousands of light years around the galaxy's interior. There are also intermediate arms and smaller structural features, and the overall picture keeps getting revised as measurements improve. Mapping the Milky Way from inside it is one of the hardest problems in astronomy, comparable in difficulty to trying to map a continent from a fixed point on the ground using only sound and shadows. You cannot step outside. You cannot gain altitude. You are embedded in the thing you are measuring, surrounded by it, unable to see its overall shape directly. The Orion Arm sits between two of these larger structures. On the side closer to the galactic center lies the Sagittarius Arm, sometimes called the Carina-Sagittarius Arm. On the side farther from the center lies the Perseus Arm, one of the galaxy's two dominant spiral features. The Orion Arm bridges the gap between them, running roughly parallel to both, stretched at a slight diagonal, extending from the direction of the constellation Cygnus on one end toward the constellation Carina on the other. For a long time, this arrangement reinforced its dismissal. If it sits between two major arms, perhaps it really is just a connecting spur, a minor bridge, a transitional feature, rather than something worth studying in its own right. That interpretation was seductive and it was wrong, but proving it wrong required technology that did not exist for most of the 20th century. Our solar system sits near the inner rim of the Orion Arm, not at its center and not at its outer edge, close to the side that faces the galactic core, roughly halfway along the arm's total length. The Sun orbits the center of the Milky Way at a distance of approximately 26,000 light years, placing it roughly halfway between the galactic center and the disk's outer edge. We are not in the dense, radiation-saturated downtown of the galaxy. We are more like a quiet suburban position, well removed from the intense gravitational chaos near the central bar and the supermassive black hole that anchors the galaxy's core. From where we sit, the nearest edge of the Orion Arm's inner boundary is only a few hundred light years away, The outer edge lies roughly 3,000 light-years in the opposite direction. In cross-section, the solar system would appear near one wall of a wide corridor of stars and gas, tucked into a relatively thin region of the arm's overall width, offset toward the galactic center side. But even that description understates the situation. The solar system is not just near the inner rim of the arm in a general sense. It sits inside a specific cavity within the arm called the local bubble, a region of space approximately 1,000 light-years across, where the density of interstellar gas is dramatically lower than the surrounding material. The local bubble was carved out roughly 14 million years ago by a series of supernova explosions from massive stars in the nearby Scorpius-Centaurus stellar association. Those explosions blasted away the local gas and dust, creating a hot, diffuse cavity that our solar system now drifts through. The interior of the bubble reaches temperatures around 1 million degrees Kelvin, but the gas is so thin that individual hydrogen atoms are separated by distances measured in kilometers. The bubble is not a void in the ordinary sense. It is more like a region where the interstellar medium has been heated and thinned to near irrelevance. Think of the Orion Arm as a vast forest stretching thousands of light years in every direction. Dense clouds of molecular gas form the thickest groves. Bright young stars blaze through clearings where stellar winds and supernova explosions have blown the canopy open. And the local bubble is a small meadow within that forest, a pocket of relative emptiness where the trees thin out and the view opens up. Our solar system sits in that meadow. We can see the surrounding forest from where we stand, but the forest extends so far in every direction that its true boundaries vanish beyond what we can observe. That meadow, the local bubble, is 1,000 light-years wide. It sounds enormous, and by any human standard it is. Light takes 1,000 years to cross it. If you could drive across the local bubble at highway speed without stopping, the journey would take roughly 11 billion years, far longer than the current age of the universe. The local bubble is incomprehensibly vast by the measure of human experience, and it is a tiny clearing inside the Orion Arm. The arm itself is roughly 3.5 times wider than the local bubble, and at least 20 times longer. The bubble occupies a small fraction of the arm's total volume. You could fit dozens of local bubbles side by side across the arm's width and hundreds along its length. The cavity we call home, the region that contains every star visible to the naked eye from Earth, every constellation humans have ever named, every nearby stellar system we have ever studied in detail, is a small pocket inside a much larger galactic feature. This is where the first real confrontation with scale arrives. Everything familiar in the night sky lives inside the Orion Arm. Sirius, the brightest star visible from Earth, sits about 8.5 light-years away. It is inside the arm. Vega, the bright blue star nearly overhead in northern summer skies, lies about 25 light-years away, inside the arm. Proxima Centauri, the nearest known star to our Sun at just over 4 light-years distant, is inside the arm. Every star in the Big Dipper, every star in Orion's belt, every star in Cassiopeia, every single point of light you can resolve with your unaided eyes on even the clearest, darkest night belongs to the Orion Arm. The stars that form the constellation Orion itself are scattered across a wide range of distances within the arm. Betelgeuse, the red supergiant marking Orion's shoulder, sits roughly 700 light-years from Earth. Rigel, the blue supergiant at Orion's foot, lies about 860 light-years away. The 3 stars of the belt range from roughly 800 to over 1,000 light-years distant. All of them are inside the Orion Arm. All of them are embedded in the same galactic structure that holds our Sun. They are not close neighbors in any meaningful physical sense. Some of them are separated from us by distances that light takes centuries to cross. But on the scale of the arm itself, they are practically next door. They all occupy the same local stretch of the same spiral feature. This is what most people miss entirely when they look up at the night sky. You are not seeing the Milky Way in general. You are seeing the inside of the Orion Arm, the soft band of light that stretches across the sky on dark nights. The thing we casually call the Milky Way is the combined glow of billions of distant stars concentrated in the galactic disk. But the individual bright stars you can pick out with your eyes are almost entirely local. They are your neighbors within the arm. The night sky is not a window onto the full galaxy. It is a view from inside one specific piece of it. Now consider what else sits within the arm beyond the naked eye stars. The Orion Nebula, one of the most photographed objects in all of astronomy, lies roughly 1,340 light-years from Earth. It is a massive stellar nursery, where new stars are actively forming right now, illuminated by a cluster of hot young stars called the trapezium at its core. The nebula spans about 24 light-years across and contains enough gas and dust to eventually form thousands of new stellar systems. It is one of the nearest large star-forming regions to our planet, and it is inside the Orion Arm. The Cygnus X region, one of the richest star-forming complexes in the entire Milky Way, lies roughly 4,600 light-years away in the direction of the constellation Cygnus. It contains some of the most massive and luminous stars known, embedded in enormous clouds of molecular hydrogen that stretch across hundreds of light-years. For years, the distance to Cygnus X was uncertain, and some astronomers believed it might belong to the more distant Perseus Arm. Precise radio measurements revealed the truth. Cygnus X is inside the Orion Arm. It belongs to our structure. The Taurus molecular cloud, a quieter but closer region of active star formation, sits about 440 light-years away. The Rho-Ophiuchi cloud complex, another stellar nursery glowing with infrared light from embedded young stars, lies roughly 460 light-years distant. The Vela molecular ridge, a chain of dense gas clouds where stars are being born across a stretch of several hundred light-years, lives inside the Arm. The Cepheus star-forming region is inside the Arm. The North American Nebula, a striking cloud of ionized hydrogen roughly 1,600 light-years away that gets its name from its shape resembling the continent, is inside the Arm. All of these objects, every one of them, exist within the same galactic structure that holds our Sun. They trace the internal anatomy of the Orion Arm, marking places where gas has piled up densely enough for gravity to win its slow battle against thermal pressure and ignite new generations of stars. The Orion Arm is not an empty corridor of space. It is alive. It is one of the most active star-forming environments in our region of the galaxy. Massive stars are being born inside it right now, collapsing out of dense molecular cores that have been accumulating material for millions of years. Other massive stars are approaching the ends of their lives, swelling into red supergiants or blue hypergiants that will eventually detonate as supernovae, seeding the Arm with heavy elements and triggering new waves of star formation in the surrounding gas. Some of the most energetic events in our galactic neighborhood, supernova explosions, the birth of neutron stars and stellar mass black holes, the violent winds of young blue giants carving cavities in the interstellar medium, all of this is happening within the Orion Arm continuously, right now, while our Sun drifts quietly through it, one quiet middle-aged yellow star among billions, carrying its small family of planets along for a ride that has already lasted 4.5 billion years. This brings us to a question that underlies everything discussed so far. If the Orion Arm is this large, this active, this full of stars and gas and violent stellar processes, why does it feel like a footnote? Why does every popular description of our cosmic address jump straight from the solar system to the Milky Way, as if nothing important exists in between? Part of the answer is psychological. Humans are not wired to think about structures they are inside of. You do not spend your day thinking about the atmosphere. You do not constantly remind yourself that you are standing on a tectonic plate. You do not feel the rotation of the Earth beneath your feet. These things are too big, too constant, too surrounding to register in ordinary awareness. The Orion Arm operates the same way. It is not hidden because it is far away. It is hidden because it is everywhere around you. You cannot see its shape because you are part of it. You cannot sense its edges because they are thousands of light years away in every direction. It does not feel like a thing you are inside because your entire frame of reference, every star and cloud and nebula you have ever observed, exists within it. Part of the answer is also historical. For decades, astronomers classified the Orion Arm as a minor spur, a small, unimpressive bridge between the real spiral arms. Galaxy maps showed it as a stubby little feature barely worth naming. The Sagittarius Arm and the Perseus Arm were the important structures. The Orion Arm was just a local wrinkle in the disk. That classification shaped how the public understood it, how textbooks presented it, how even scientists talked about it in casual descriptions of galactic structure. Minor spur, local spur, Orion spur. The vocabulary itself carried a dismissal built into it. But that classification was based on incomplete data. Astronomers were measuring the arm using only the stars and gas clouds they could see from inside it, which is like trying to measure the full length of a hallway while standing in the middle with the lights off and a flashlight that only reaches 10 feet in front of you. They could see nearby features clearly. They could detect bright, massive stars at moderate distances. but the full extent of the arm remained hidden behind curtains of interstellar dust that block visible light and behind the fundamental difficulty of measuring accurate distances to objects embedded in the same structure you are trying to map. It took a revolution in measurement technology to reveal what the Orion Arm actually is: radio telescopes that could see through dust, space missions that could track the precise positions and motions of over 1 billion stars, techniques that could measure distances to individual star-forming regions with accuracies that previous generations of astronomers could only dream about. When those measurements finally came in, the Orion Arm refused to stay small. The first major surprise arrived in 2013, when a team led by researchers at the Purple Mountain Observatory in China used very long baseline radio interferometry to measure precise distances to bright maser sources, natural microwave beacons associated with regions of massive star formation deep inside molecular clouds. These masses are produced when clouds of gas containing trace molecules like water and methanol amplify microwave radiation into intense narrow beams that radio telescopes can detect across thousands of light years. By observing these masses from multiple radio telescopes spread across continents and measuring the tiny shifts in their apparent positions as the Earth orbits the Sun, astronomers can calculate their distances through the same parallax method that land surveyors use on Earth, only scaled up to galactic proportions. The measurements revealed that the Orion Arm extended much farther than anyone had previously mapped. Stars and gas clouds that had long been assumed to belong to the more distant Perseus Arm turned out to be part of the Orion Arm instead. The arm was not a short, stubby spur. It stretched far enough and showed enough internal structure that the team concluded it might be a branch of the Perseus Arm, or possibly an independent arm segment in its own right. The 2013 paper was the first crack in the old picture, the first serious evidence that our local spiral feature was being dramatically underestimated. In 2016, the same research group published follow-up results that pushed the arm's known length to at least 20,000 light-years. They identified and measured 8 new maser sources within the Orion Arm and found that the arm's pitch angle, the tilt of its spiral curve relative to circles centered on the galactic core, and its rate of star formation were both comparable to those of the galaxy's major spiral arms, like Sagittarius and Perseus. The Orion Arm was not a minor feature. It was, in the words of the researchers, reasonably described as the 5th major structural feature of the Milky Way. Then the Gaia spacecraft entered the picture and changed everything again. Launched by the European Space Agency in 2013, Gaia spent over 11 years scanning the sky and measuring the precise positions, distances, and motions of nearly 2 billion stars before completing its observation phase in January of 2025. Its data releases transformed the study of galactic structure in ways that no single ground-based survey could match. Multiple independent research teams used Gaia data to trace the distribution of young stars, open clusters, and interstellar dust across the Milky Way disk, and their results converged on the same conclusion. A team using Gaia's early data estimated the Orion Arm's length at over 25,000 light-years, consistent with the maser parallax measurements. A separate team, led by researchers at the Université Côte d'Azur in France, used Gaia data to map hundreds of thousands of young blue stars and confirmed the same extended picture. The Orion Arm, once dismissed as a minor spur, was revealing itself as a substantial spiral structure with properties that rival the galaxy's traditionally recognized major arms. Gaia even showed that the Milky Way's spiral arms in general may be less sharply defined than older models assumed, with the boundaries between arms appearing more ragged and complex than the elegant textbook spiral suggested. These discoveries did not just change a number on a chart, they changed what the Orion Arm means. It went from being a minor background feature, something you glance past on a galaxy diagram on the way to more impressive structures, to being a genuine galactic structure, a full-scale spiral arm segment containing billions of stars, active star-forming regions rivaling anything in the Perseus or Sagittarius arms, and an internal architecture complex enough that scientists are still mapping its details today. The textbooks that called it a minor spur were not lying. They were measuring a shadow. They were seeing only the nearest, brightest pieces of a structure that extends far beyond what their instruments could reach. The Orion Arm is not minor. It is not a footnote. It is the galactic structure that contains everything humans have ever called home, and its true scale is far more striking than even this revised picture suggests. The solar system feels large. It should. It took the Voyager, one spacecraft, traveling at roughly 17 kilometers per second, over 35 years, just to reach the boundary where the solar wind gives way to interstellar space. The distance from the Sun to Neptune, the outermost major planet, is approximately 4.5 billion kilometers. If you drove that distance at highway speed without stopping, the trip would take over 5,000 years. The solar system, measured out to the theoretical outer edge of the Oort cloud, may extend as far as 2 light-years from the Sun in every direction. That is an enormous volume of space by any standard a human being can personally experience. Now place that volume inside the Orion Arm. The arm is roughly 3,500 light-years wide. The solar system's full extent, out to the most distant hypothetical reaches of the Oort cloud, spans about 4 light-years across. That means you could line up nearly 900 solar systems side by side across just the width of the Orion Arm. Not its length, its width, the narrow dimension. And 900 is a generous estimate, because most of the solar system's meaningful structure, the region containing all 8 planets, fits within a diameter of roughly 10 light-hours, which is so small relative to the arm's width that it vanishes entirely from any map drawn at galactic scale. Go further. The Orion Arm stretches at least 20,000 light-years from end to end, and some measurements push it closer to 25,000. At that scale, the solar system does not merely shrink, it ceases to be representable. If you drew the Orion Arm as a rectangle on a piece of paper, say 30 centimeters long by 5 centimeters wide, the solar system would not be a dot. It would not be a pixel. It would be smaller than a single atom of ink on the page. You could not mark it even if you tried. This is the first real confrontation with what it means to live inside this structure. The solar system is not small in any way a human can intuitively understand. It is simply operating at the wrong scale to register against the arm that contains it. The nearest star to our Sun is Proxima Centauri, just over 4 light-years away. That distance is already so extreme that no human technology currently exists that could cross it within a single lifetime. The fastest spacecraft humanity has ever launched would need roughly 70,000 years to reach it. And yet that distance, the gap between our Sun and the closest neighboring star, amounts to approximately 1/5,000th of the arm's length. Imagine standing on one end of a runway 5 kilometers long. The distance to Proxima Centauri, the gap that currently represents the absolute frontier of human ambition in interstellar travel, would be a single step. 1 meter on a 5-kilometer path. Extend the picture to other well-known nearby stars. Sirius, the brightest star in the sky, sits 8.5 light-years away. On that same 5-kilometer scale, that is roughly 2 steps. Vega, 25 light-years distant, is about 12 steps. Arcturus, one of the most luminous stars in the northern sky, lies 37 light-years away, about 18 steps. All of these stars, the brightest and most familiar objects in the human sky, represent distances so trivial relative to the Orion Arm that they barely qualify as motion along the arm's length. And yet these distances already defeat us completely. We cannot cross them. We cannot communicate across them in any reasonable time frame. The fastest possible signal, a beam of light, takes 4 years to reach Proxima Centauri, 8.5 years to reach Sirius, 25 years to reach Vega. Each of these trips is already beyond the horizon of practical human activity, and each of them covers a distance so tiny relative to the arm that it rounds to nothing. Consider how Voyager 1 fits into this picture. It launched in 1977. It has been flying away from Earth continuously for nearly 5 decades. It is the most distant human-made object in existence, and in all that time, traveling at 17 kilometers per second, it has covered approximately 0.0027 light-years. Compare that to the arm's width of 3,500 light-years. Voyager's entire journey so far amounts to less than 1/millionth of the distance across the narrow dimension of the structure we live in. If the Orion Arm's width were the distance from New York to London, Voyager 1 would not have made it out of the departure terminal. About 4 meters of pavement. That is the fastest object humanity has ever flung into space, and it has not even begun to matter against the arm's scale. This is where the psychological compression becomes visible. The human mind defaults to treating nearby stars as though they represent the scale of our galactic environment. We say the nearest star is 4 light-years away, and that feels like the edge of our local world. We think of stars within a few dozen light-years as our neighborhood, but our neighborhood is a pinprick. The arm extends thousands of times farther than the distances we think of as vast. The comfortable language of nearby and far away collapses completely when you try to apply it inside a structure this large. Our Sun belongs to no star cluster. It drifts through the arm as a field star, unattached to any gravitationally bound group. But other stars in the Orion Arm do belong to clusters. The Pleiades, that small bright cluster visible in winter skies, sits roughly 440 light-years away. The Hyades, an older and closer cluster, lies about 150 light-years from Earth. These clusters contain hundreds of stars each, born together from the same collapsing gas cloud millions of years ago, still moving through space as coherent groups. These clusters are inside the arm. They are specks inside it. The Pleiades, a cluster you can see with your unaided eyes, one that humans have used for navigation and storytelling for thousands of years, occupies a volume roughly 43 light-years across. That is about 1% of the arm's width. 1%. The entire cluster, all its stars and gas and gravitational influence, amounts to a tiny clot of material embedded in one small region of the arm's much larger body. And here is where the arm begins revealing just how much it actually contains. In 2020, a team of astronomers led by João Alves at the University of Vienna, Catherine Zucker at the Harvard-Smithsonian Center for Astrophysics, and Alyssa Goodman at Harvard made a discovery that redrew the interior map of the Orion Arm in one stroke. Using three-dimensional dust mapping techniques powered by precise distance measurements from the Gaia spacecraft, they identified a structure no one had seen before. A gigantic undulating chain of dense gas clouds stretching roughly 9,000 light-years through the arm's interior, connecting many of the most famous star-forming regions in our galactic neighborhood into a single coherent wave-shaped feature. They named it the Radcliffe Wave after the Harvard Radcliffe Institute where the discovery was made. The Radcliffe Wave threads through the Orion Arm like a spine. It connects the Orion molecular cloud complex to the Taurus clouds, the Perseus clouds, the Cepheus star-forming region, the North American Nebula, and the Cygnus star-forming complexes into one continuous sinusoidal ribbon of gas. The wave oscillates above and below the galactic plane, rising as high as 500 light-years above the disk mid-plane in some places and dipping below it in others. Its closest point passes within roughly 500 light-years of our Sun. It is, in a very real sense, the backbone of the nearest spiral arm. For years, astronomers had studied these star-forming regions individually. The Orion Nebula was one object, Taurus was another, Perseus was a third. They were treated as separate features, catalogued independently, analyzed in isolation. The Radcliffe Wave revealed that they are all part of a single connected structure, a chain of stellar nurseries strung along the arm like beads on a wire, linked by gas and dust and the underlying gravitational field of the spiral arm itself. The discovery did not just change the map of the arm's interior, it changed the conceptual picture of what the arm is, revealing it as a dynamically structured environment with large-scale coherent features extending for thousands of light-years. And in February of 2024, the story deepened. A team led by researchers at Harvard published a paper in Nature showing that the Radcliffe Wave is not just shaped like a wave, it moves like one. Using updated Gaia data to track the three-dimensional motions of young star clusters born within the wave's gas clouds, the researchers demonstrated that the entire 9,000 light-year structure is oscillating. It undulates up and down through the galactic plane over time, driven by the gravitational pull of the Milky Way's disk. The wave ripples through space the way a traveling wave moves, through a stadium full of people, rising and falling in sequence as the disturbance propagates along the structure's length. No one knows what caused the wave. No one knows what initially displaced the gas from the galactic midplane to set the oscillation in motion. Some researchers have speculated about a past collision with a massive gas cloud or a dark matter substructure passing through the disk. Whatever the trigger, the result is a dynamic living feature inside the Orion Arm, a structure that moves on timescales of millions of years, giving birth to new stars along its entire length as it ripples through the galactic plane. And here is something that makes the Radcliffe Wave feel uncomfortably personal. In early 2025, a team published a study in the journal Astronomy and Astrophysics showing that the solar system did not merely drift near the Radcliffe Wave, it passed directly through it. Sometime during the Middle Miocene epoch, roughly 12 to 15 million years ago, the Sun's orbit through the galaxy carried the entire solar system through the dense gas of the wave's Orion region. The encounter likely lasted several million years, during which the solar system would have been immersed in the denser interstellar environment of a star-forming cloud complex. This was not a gentle brush. The passage would have compressed the heliosphere, the protective bubble of solar wind that surrounds our planetary system, pushing interstellar material closer to the inner solar system than it normally reaches. The researchers suggested that increased dust from this galactic encounter could have penetrated Earth's atmosphere, potentially leaving traces of radioactive isotopes from nearby supernovae in geological sediment layers. The evidence is not yet confirmed, partly because current detectors may not be sensitive enough to pick up the signal, but the implication is striking. The Orion Arm is not just the abstract structure that contains us. It has physically interacted with our planet. Its gas clouds have touched our solar system. Its supernovae may have left chemical fingerprints in Earth's rocks. The arm is not a backdrop. It is an environment that has reached down and altered the conditions on the surface of our world. 9,000 light years. A single connected structure of gas and newborn stars oscillating through the interior of our spiral arm. And we only discovered it existed in 2020 because we finally had the technology to see it. We only discovered that our solar system had passed through it in 2025. This is what the Orion Arm contains. Not just scattered stars and isolated nebulae, but enormous coherent structures spanning thousands of light years, hiding in plain sight because we lacked the three-dimensional mapping tools to recognize them. The arm is not a simple corridor of stars. It is a layered dynamic environment with internal architecture that scientists are still uncovering. The Radcliffe Wave is the most dramatic recent example, but it is not the only large-scale feature inside the arm. The arm contains vast complexes of molecular gas, regions where hydrogen exists not as individual atoms but as molecules packed into cold, dense clouds with temperatures just a few degrees above absolute zero. These molecular clouds are the raw material for star formation. They fill the arm's interior in enormous concentrations, some of them spanning hundreds of light years across and containing enough mass to form thousands of stars. The Orion Molecular Cloud Complex, the parent structure of the Orion Nebula, stretches roughly 240 light years from end to end and contains roughly 200,000 times the mass of our Sun in gas and dust. Stars are forming throughout this complex right now, collapsing out of dense cores buried inside the cloud's darkest, coldest regions. The Orion Nebula itself is just the most visible piece of a much larger system. The Cygnus X complex, which lies near one end of the Orion Arm in the direction of the constellation Cygnus, is even more massive. It contains millions of solar masses of molecular gas spread across a region several hundred light years wide. It is one of the most prolific star-forming regions in the entire galaxy. Some of the most massive stars known, blue supergiants burning through their fuel at rates millions of times greater than our Sun, were born inside Cygnus X within the last few million years. This region alone has shaped the interstellar environment of the Orion Arm's far end through its intense radiation, powerful stellar winds, and the supernova explosions of its earliest and most massive members. Between these major complexes, the arm is threaded with diffuse interstellar gas, streams of neutral hydrogen atoms that emit faint radio waves at a wavelength of 21 centimeters. This gas traces the arm's overall shape at the largest scales. It is one of the primary tools astronomers use to map spiral structure because neutral hydrogen is abundant and its radio emission passes through the dust that blocks visible light. Radio surveys of the 21 centimeter line have been mapping the Milky Way's arm since the 1950s, and they remain essential for understanding the arm's full extent. Dust fills the arm as well. Microscopic grains of carbon and silicate produced in the outer layers of dying stars and scattered through the interstellar medium accumulate in the densest parts of the arm. These grains absorb and scatter visible light, creating the dark lanes and patches visible in long exposure photographs of the Milky Way. The dust is both a nuisance and a tool. It blocks views of distant stars and structures, making the arm harder to map in visible light. But it also glows in infrared. By mapping its thermal emission, astronomers can trace the arm's dense regions, even where optical telescopes see nothing. This brings us to a realization that changes how the arm should feel. The Orion Arm is not mostly empty space dotted with occasional stars. By galactic standards, it is a dense structured environment. The average density of the interstellar medium within a spiral arm is several times higher than the density between arms. Gas piles up along the arm's length, compressed by the spiral density wave that maintains the arm's overall shape. Stars form preferentially within arms. Because of this compression, the brightest, hottest, Most massive stars in the galaxy, the O-type and B-type giants that burn blue-white and live only a few million years, are found almost exclusively within spiral arms. They are born inside the arm's dense gas and die before they can drift away. These massive stars are the lighthouses of galactic structure. They are so bright that they can be seen from enormous distances, and their concentration within spiral arms is one of the primary ways astronomers identify arm locations in other galaxies. When you look at a photograph of a distant spiral galaxy and see its arms traced in brilliant blue-white light, you are seeing the collective glow of O-type and B-type stars, the same kinds of stars that populate the Orion Arm and trace its structure. Within our arm, these massive stars cluster into groupings called OB associations, loose collections of young bright stars that form together from the same giant molecular cloud. The Orion OB1 association, centered on the constellation Orion, is one of the nearest and best studied. It contains several subgroups of stars spanning ages from roughly 12 million years down to less than 1 million years, tracing multiple generations of star formation within the same region of the arm. The Scorpius-Centaurus association, which lies closer to the Sun, is another major OB grouping within the arm. It was the supernova explosions of massive stars in this association that carved out the local bubble roughly 14 million years ago. These associations are enormous. Scorpius-Centaurus spans roughly 400 light-years across. Orion OB1 stretches across a similar distance. Each one is a significant substructure within the arm, a region where dozens of massive stars have formed and exploded over millions of years, reshaping the surrounding gas and triggering cascading waves of new star formation. And yet even the largest of these associations is small compared to the arm. 400 light-years is about 11% of the arm's width and barely 2% of its length. The associations are significant features, but they are features within a much larger feature. They are rooms inside a building that stretches far beyond what any single room can reveal. The massive O-type and B-type stars are only the brightest inhabitants of the arm. They are not the most numerous. For every blazing blue giant, there are thousands upon thousands of smaller, dimmer stars that no human eye will ever see. Red dwarfs, the smallest and coolest hydrogen-burning stars, make up roughly 70% of all stars in the Milky Way. They are so faint that even the nearest one, Proxima Centauri, is invisible to the naked eye, despite being the closest star to our Sun. The Orion Arm contains billions of these dim red embers scattered throughout its volume, burning steadily for tens of billions of years. Many of them are likely orbited by planets, and almost all of them are completely unknown to us individually. We have catalogued the bright hot stars within a few thousand light-years. We have identified many of the clusters and associations and nebulae, but the vast majority of the arm's stellar population, the ordinary, quiet, long-lived stars that make up the bulk of its mass, have never been individually observed beyond the nearest few hundred light-years. They exist in numbers so large that even modern surveys can only sample a fraction. Gaia catalogued nearly 2 billion sources across the entire sky, and that extraordinary number still represents only a small percentage of the total stellar population of the Orion Arm. Alone, current estimates suggest the arm contains somewhere in the range of several billion stars along its full extent. Each of those stars is a furnace. Each one has a gravitational domain. Many of them have planetary systems. Some fraction of those planetary systems may include rocky worlds in zones where liquid water could persist on the surface. We do not know how many. We cannot see them. They are too distant and too faint. But the statistical certainty is that the arm contains vast numbers of worlds we have never detected, orbiting stars we have never named, scattered throughout a volume of space we have only partially mapped. A single planetary system, even a rich one like our own with 8 planets and hundreds of moons, is like a pebble tossed into a lake the size of a continent. It exists, it is real, and it is utterly lost in the scale of the water around it. Every object we have discussed, the Radcliffe Wave, the Cygnus X complex, the Orion molecular cloud, the Scorpius-Centaurus association, the local bubble itself, is a major, well-studied, scientifically important structure. Each one represents decades of astronomical research. Each one fills journals and conferences and doctoral dissertations. And each one is a subcomponent of the Orion Arm, a piece of the arm's internal anatomy, a feature within a structure that itself sits inside a much larger galaxy. The arm contains all of them simultaneously. It has room for all of them simultaneously, and it has room for vastly more that we have not yet catalogued or detected. The Orion Arm approximated very roughly as a flattened rectangular slab about 20,000 light-years long, 3,500 light-years wide, and 1,000 light-years thick, encloses a volume of roughly 70 billion cubic light-years. That number is already meaningless in human terms, but compare it to the solar system, the region of space dominated by our sun's gravity, out to the estimated outer edge of the Oort cloud, fills a sphere roughly 4 light-years in diameter. Its volume is about 33.5 cubic light-years. The Orion Arm's volume is approximately 2 billion times larger than the volume of our solar system. If the arm were a football field, the solar system would not be a grain of sand sitting on the turf. It would be something far smaller than a grain of sand, something closer to a single bacterium riding a dust mote drifting through a cathedral. 2 billion times. That ratio is the distance between the scale of everything you know and the scale of the galactic structure that contains it. The solar system, with all its planets and moons and comets and asteroids and the vast empty stretches between them, occupies less than 1/2 billionth of the arm's volume. This is not a metaphor. This is the actual geometric relationship between our home planetary system and the galactic structure that holds it. The solar system is not a significant fraction of the Orion Arm. It is not a notable feature. It is not a landmark. It is a point, a dimensionless dot that falls below the resolution of any reasonable map of the arm's structure. We are not lost in the galaxy, we are lost in the arm, and the arm is not even the galaxy. There is a moment in the history of astronomy that captures how long it took humanity to begin understanding this. In December of 1951, at the 86th meeting of the American Astronomical Society, an astronomer named W. Morgan from Yerkes Observatory in Williams Bay, Wisconsin, presented something no one had seen before. He did not show a graph. He did not project a photograph. He built a physical model, a wooden board roughly the size of a tabletop, into which he had driven 25 nails. Atop each nail sat a small white cotton ball. Each ball represented the measured position of an OB association, a grouping of hot, massive, young stars whose distances Morgan and his colleagues had painstakingly calculated using photometric techniques. When the audience looked at the board, the cotton balls were not scattered randomly. They fell into 3 distinct linear groupings, 3 parallel bands of bright young stars stretching across the sky. Morgan told the audience they were looking at 3 spiral arms of the Milky Way. The nearest band, the one passing closest to the sun, would later be named the Orion Arm. The audience reaction was unusual for a scientific conference. Several attendees reportedly wept. They were looking at the first direct evidence of spiral structure in our own galaxy. They were seeing, for the first time, that the stars around us were not randomly distributed through space, but were organized into a coherent large-scale pattern. They were, in that moment, understanding for the first time something about the large-scale structure of the place they called home. Morgan's 25. Nails traced the shape of an arm that would take another 7 decades to measure properly. What he saw that evening was a rough outline, a first sketch of a structure whose full dimensions remained hidden for the rest of the 20th century. The technology to complete his sketch would not arrive until the 21st century. The challenge that limited Morgan and every astronomer who came after him is dust, interstellar dust. Tiny grains of carbon and silicate scattered throughout the arm's gas absorb and scatter visible light. A star 10,000 light-years away might be completely invisible to an optical telescope, not because it is faint, but because the dust between us and the star has absorbed its light entirely. In the densest regions of the arm, where molecular clouds pile up along the spiral structure, dust can block everything behind it for thousands of light-years. The galactic center itself, sitting 26,000 light-years away, is entirely invisible in optical wavelengths. If you pointed the largest optical telescope on Earth directly at the heart of the Milky Way, you would see nothing but dark clouds. This dust is not distributed evenly. It concentrates within the spiral arms, exactly where the stars and gas are densest. The very structures astronomers are trying to map are also the structures that block the view. The Orion Arm's own gas and dust prevent us from seeing its full extent in visible light. We can observe nearby stars and nebulae clearly, but beyond a few thousand light-years, the arm's interior becomes increasingly opaque. Looking along the arm's length towards Cygnus at one end, or Carina at the other, the view is even worse because the dust accumulates along the entire line of sight, stacking up over enormous distances. This is why the arm was underestimated for so long. Early astronomers mapped what they could see. They counted bright stars, identified nebulae, and measured the positions of the nearest objects. Where the stars thinned out and the dust took over, they assumed the structure ended. The Orion Arm appeared to be a short, stubby feature because the visible evidence ran out after a few thousand light years in every direction. The arm did not end there. The view ended there. Mapping the Orion Arm from inside the Milky Way is like trying to map a continent from a single fixed point on the ground, using only echoes and shadows. You cannot fly above the terrain. You cannot move to a different vantage point. You are stuck in one place, surrounded by the thing you are measuring, and most of it is hidden behind obstacles you cannot see through. The challenge is not merely difficult, it is one of the hardest observational problems in all of astronomy. And the fact that we have solved it as well as we have represents one of the great achievements of modern science. The solution came in stages. Radio telescopes bypass the dust by operating at wavelengths long enough to pass through it undisturbed. The 21-centimeter emission from neutral hydrogen revealed the arm's broad contours as early as the 1950s, giving astronomers a map of the gas distribution even where the stars were invisible. Infrared telescopes detected the thermal glow of dust itself, tracing the dense warm regions where star formation was underway. And then very long baseline radio interferometry arrived, allowing researchers to measure the precise parallax distances to maser sources with accuracies that completely transformed the picture. The most recent and most comprehensive revolution came from the Gaia satellite, which measured the positions and motions of nearly 2 billion stars with a precision that previous generations of astronomers could not have imagined. Gaia's data allowed researchers to build three-dimensional maps of the stellar distribution in our galactic neighborhood with an accuracy that extends reliably out to several thousand light years in every direction from the sun. It was Gaia data that made the Radcliffe wave visible. It was Gaia data that confirmed the arm's extended length. It was Gaia data that allowed scientists to place the sun within the arm's structure with confidence rather than estimation. And the arm is still revealing itself. We have mapped only a fraction of its full extent with high precision. The regions closest to the sun are well studied. The features within a few thousand light years have been catalogued and measured with increasing accuracy. But the arm extends far beyond our current high-precision mapping. Its far end, stretching toward the constellation Carina and beyond, remains poorly constrained. Dust blocks the view. Distance measurements become less reliable. Entire star-forming complexes may exist in the arm's more distant reaches that we have not yet identified. The arm we think we know may be even larger, even more complex, even more populated than current data reveals. What scientists want to understand next is how the Orion Arm fits into the overall spiral structure of the Milky Way. The galaxy's spiral pattern is generated by density waves, regions of higher gravitational potential that sweep through the disk over timescales of hundreds of millions of years. Stars and gas pile up as they pass through these waves. The way traffic slows in bunches in a construction zone even as individual cars continue moving through it. The spiral arms are not rigid structures. The stars within an arm are not permanently attached to it. They flow through the arm over millions of years, spending a period of elevated density in the arm's compressed environment before drifting out the other side. Our sun has made this journey multiple times. Over its 4.5 billion year life, it has orbited the galactic center roughly 20 times, each orbit carrying it through the density waves that generate the spiral arms. During each pass through an arm's denser gas, the conditions in our local interstellar environment changed. The frequency of nearby star formation increased. The rate of supernova explosions in our neighborhood fluctuated. The density of the interstellar medium through which the heliosphere moved varied. The sun's passage through the Radcliffe wave 12 to 15 million years ago was one such encounter, and its effects may have been recorded in Earth's geology. This is one of the genuinely open scientific questions about the Orion Arm. How many times has the solar system passed through dense regions of the arm's interior? And what effects did those passages have on the Earth and on life? The connection between galactic dynamics and planetary environments is an active area of research. Some scientists have proposed that the rhythm of mass extinctions in Earth's fossil record might partially reflect changes in the galactic environment as the solar system moves through regions of varying stellar density and cosmic ray flux. The evidence is circumstantial, and the proposals remain controversial, but the underlying physics is real. The galactic environment changes as the sun moves through the arm, and a changing galactic environment can influence conditions on Earth. Another open question concerns the arm's relationship to the galaxy's major structural features. Is the Orion Arm truly an independent spiral arm segment, or is it physically connected to one of the major arms at some point along its length? Current data supports the picture of an independent structure, but the boundaries are not sharp. The transition from the Orion Arm to the adjacent Sagittarius and Perseus arms is not a clean edge. It is a gradual change in stellar density, a blurring of boundaries that reflects the Milky Way's complex and somewhat irregular spiral pattern. The galaxy does not look like the perfect textbook spiral illustrated in introductory astronomy books. It is messier than that, with branches and spurs and connections that resist easy classification. The question of how many spiral arms the Milky Way has, and how to define and count them, remains genuinely unsettled. Different research groups using different traces, different radio surveys, different catalogues of young stars and star clusters, sometimes arrive at different pictures of the galaxy's large-scale structure. This is not a failure of science. It is the expected difficulty of mapping a complex three-dimensional structure from a single embedded point with limited sight lines. The Milky Way does not cooperate with the human desire for clean, simple answers. What is not in doubt is the scale. The Orion Arm, however exactly you define its boundaries, and whatever its precise relationship to the galaxy's other structural features, is enormous. 20,000 to 25,000 light-years long, 3,500 light-years wide, containing billions of stars, filled with gas clouds spanning hundreds of light-years, hosting active star formation regions as prolific as any in the galaxy, threaded by a 9,000 light-year wave of oscillating molecular gas that connects our most familiar stellar nurseries into a single dynamic structure, and containing, buried in a 1,000 light-year clearing near its inner rim, the one star and the one planetary system that has ever asked any of these questions. Think about what that means for the conventional picture of our cosmic address. We say we live in the Milky Way, and that answer feels complete. It sounds like the full picture. Earth, solar system, Milky Way. 3 steps from your front door to the cosmos. Done. But that answer skips something enormous. Between the solar system and the full Milky Way sits a structure 5,000 times longer than our solar system, containing billions of other stars, each one as real and as burning as our own, most of them completely unknown to us, many of them surrounded by their own planets and moons, and possibly their own versions of pale blue dots where something might be looking up at a sky full of other arm-resident stars and feeling exactly the same thing we feel. When we look up and assume the sky belongs to us, the sky belongs to the arm. Every star in it is a fellow resident of the same galactic structure, and most of them are so far away that their light takes centuries or millennia to reach us. We share a home with billions of stars and will never visit any of them. We will never send a message that arrives at the arm's far end within a human civilization's lifespan. We are neighbors in name only, connected by structure, separated by scale. This is the paradox of the Orion Arm. It is home. It is genuinely, physically, structurally, the galactic environment that contains our sun and our planet, and everything we have ever known. But it is a home so large that the word loses its meaning. Home implies familiarity. It implies a space you can know, can navigate, can hold in your mind as a complete picture. The Orion Arm defeats all of that. It is a home you cannot see the edges of. A home you cannot cross in 100,000 lifetimes. A home that contains more stars than you could count if you spent every second of your life doing nothing else. And this brings us to the final, most unsettling layer. The Orion Arm is not even a large structure by galactic standards. The Perseus Arm, which lies just outward from us, stretches more than 60,000 light-years along its arc. The Scutum Centaurus Arm wraps even farther around the galaxy's interior. The full Milky Way disk with all its arms and interarm regions spans 100,000 light-years or more. The Orion Arm at 20 to 25,000 light-years is one of the smaller spiral features in the galaxy. This means the structure that already makes our solar system feel invisible is itself a modest feature within a much larger system. The arm that dwarfs everything we know is dwarfed in turn by the galaxy that contains it. And the galaxy is dwarfed by the local group. And the local group is dwarfed by the supercluster. The hierarchy of scale does not stop. It keeps climbing, and at every level, the structures below shrink into insignificance. But there is something specific about the Orion Arm that makes its scale feel different from the abstract vastness of galaxy clusters and superclusters. Those larger structures are far away. They are out there, beyond the reach of any personal connection. The Orion Arm is not out there. It is the thing you are inside of right now. It is the immediate galactic environment. The gap between you and the arm is zero. You are part of it. Your atoms were forged in stars that lived and died within it. The iron in your blood was manufactured in a supernova that exploded somewhere inside this arm billions of years ago. The calcium in your bones came from a dying star that shed its outer layers into the arm's interstellar medium. You are not observing the arm from outside. You are made of it, and yet you cannot feel it. You cannot sense its boundaries. You cannot perceive its shape. It is too large, too surrounding, too encompassing to register in ordinary awareness. It is the ultimate invisible environment, a structure vast enough to contain billions of stars and yet subtle enough that a species living inside it can go its entire history without knowing it is there. Astronomers discovered the Orion Arm less than a century ago. For the vast majority of human existence, no one on Earth knew that the stars in the sky traced a specific galactic structure. No one knew that our sun sat near the inner rim of a spiral arm. No one knew that the bright band of the Milky Way was a disk of stars seen from inside, let alone that within that disk. Our local region constituted a defined, measurable, nameable piece of spiral architecture. We found it. We mapped it. We measured its dimensions. We upgraded it from a minor spur to a legitimate arm segment. We discovered that it contains a 9,000 light-year oscillating wave of gas and newborn stars running through its interior like a backbone. We placed our sun within it at a specific, well-determined location. We traced its connections to the neighboring arms and fit it into the larger pattern of the Milky Way's spiral structure. And after all of that, the most striking fact remains the simplest one. The Orion Arm is the part of the Milky Way that we call home. It is not the whole galaxy. It is not even one of the galaxy's most prominent features. It is our local arm, our immediate galactic neighborhood, the thing between us and the larger galaxy. And it is already, by itself, without invoking anything beyond it, so large that our solar system vanishes inside it. You do not need to zoom out to the observable universe to feel the weight of cosmic scale pressing down on human significance. You do not need to invoke 2 trillion galaxies or 93 billion light-years. You just need to understand what it means to live inside a single spiral arm of a single galaxy, a structure 20,000 light-years long, 3,500 light-years wide, containing billions of stars you will never see and distances you will never cross, stretching in every direction far beyond the reach of your fastest signal and your most ambitious imagination. The Orion Arm is home, and home is so much larger than we ever thought that the word barely applies anymore. Not because the universe is vast, although it is, but because even the local part of it, even the piece we casually label ours on a diagram, is already vast enough to make us almost anonymous inside it. That is the true scale of the Orion Arm. Not a label on a map, not a footnote beneath a galaxy illustration, a real physical galactic structure large enough to hold everything humanity has ever known and still stretch on for thousands of light years beyond, filled with stars and gas and light we will never reach. A structure large enough to make the solar system feel lost inside the part of the galaxy we call home. Every star you have ever wished upon burns somewhere inside it. Every constellation you have ever traced lives within its borders. And it extends so far beyond those familiar lights that even at the speed of light, you would need 20,000 years to see it all. Researchers are not done with the Orion Arm. The next generation of observations, combining the completed Gaia catalogue with data from radio telescopes like the Very Long Baseline Array and next-generation infrared surveys, aims to extend precise distance measurements to the arm's far reaches, particularly the poorly mapped regions toward Carina in the southern sky. If the arm's length turns out to be closer to 25,000 light-years or more, the revision from minor spur to major arm segment will be even more dramatic than the current picture already suggests. Scientists also want to understand the Radcliffe wave more deeply. The oscillating backbone of our arm represents a type of large-scale structure that was simply invisible before three-dimensional dust mapping became possible. Researchers want to know whether similar waves exist in other spiral arms, whether such waves are a common feature of galaxy dynamics or a peculiarity of the local environment, and what long-term effects the wave's oscillation might have on the rate and pattern of star formation along its length. The questions about what triggered the wave and whether the solar system's passage through it left any measurable trace in Earth's geology or in the isotope record of ancient cosmic dust remain open and actively investigated. The big picture question, the one that sits behind all of these detailed measurements, is what the Milky Way's spiral structure actually looks like. We live in a galaxy, and we still cannot draw a reliable map of it. The individual arms, their lengths, their pitch angles, whether they are continuous or broken into segments, how they connect to the central bar, these remain subjects of active debate. The Orion Arm is a window into that larger problem. Every precise measurement of a maser source in the Orion Arm, every new cluster distance from Gaia, every infrared survey of molecular clouds in the Arm's far reaches, adds a data point to the incomplete map of our galaxy. We are inside the Orion Arm. We have always been inside it. We will always be inside it for as long as humanity exists on this planet. And now, for the first time in human history, we are beginning to understand just how deeply buried we really are. The Arm surrounds us. It made us. Its supernovae seeded the molecular cloud that collapsed to form our sun. Its gas supplied the raw material for our planet. Its stellar radiation shaped the photochemistry of Earth's early atmosphere. We are not visitors inside the Orion Arm. We are products of it. And the Arm, indifferent to all of that, continues what it was doing billions of years before we arrived. Forming stars, losing stars to supernovae, sculpting its molecular clouds into new generations of suns and planets, oscillating slowly through the galactic plane, drifting with its galaxy around the local group. The Arm does not know we are here. It does not need to. It is already one of the most remarkable structures in the observable universe, and it does not require our awareness to be so. If you found this exploration of our galactic neighborhood as striking as the science behind it, taking a moment to like and subscribe helps more people find these deep dives into the structures that surround us without our knowing. There is no shortage of things to uncover, and most of them, like the Orion Arm, have been hiding in plain sight the whole time. To understand why the Orion Arm was so easy to overlook for so long, it helps to understand the broader history of how astronomers came to realize that the Milky Way itself is a spiral galaxy. For most of human history, the nature of the Milky Way was not understood at all. The soft band of diffuse light stretching across the sky was recognized as a concentration of stars by Galileo in 1610, when he turned his first telescope toward it and resolved the glow into countless individual points of light. But what that meant, what it implied about the structure of the cosmos, remained deeply unclear for centuries after. The first serious attempt to map the shape of the galaxy came from William Herschel in the late 18th century. Herschel counted stars in different directions across the sky and concluded that the Sun sat near the center of a flattened, disc-shaped system. His estimate of the galaxy's shape was not far wrong, but his conclusion about the Sun's position was deeply mistaken. He placed us near the center because he could not correct for the dust that dims and hides distant stars. In the dusty plane of the galaxy, stars thin out at large distances, not because the galaxy ends there, but because the view runs out. Herschel was seeing the edge of the transparent region, not the edge of the galaxy. This fundamental confusion persisted for over a century. By the early 20th century, astronomers had developed increasingly sophisticated methods for measuring stellar distances and mapping stellar distributions. Jacobus Kapteyn, a Dutch astronomer, produced the most careful statistical analysis of the stellar distribution available in the early 1900s. And he also concluded that the Sun sat near the center of a moderately sized stellar system, roughly 30,000 light-years across. The Sun was special. It was central. The galaxy was small. Both conclusions were wrong. The correction came from Harlow Shapley, working at the Mount Wilson Observatory in California in the late 1910s. Shapley studied globular clusters, dense spherical collections of hundreds of thousands of old stars that orbit the Milky Way in a halo surrounding the disk. By measuring the distances to these globular clusters, using a special type of pulsating star called a Cepheid variable as a distance indicator, Shapley discovered that they were not distributed symmetrically around the Sun. They were concentrated in the direction of the constellation Sagittarius, in a region far from the Sun in the direction of the galactic center. Shapley correctly concluded that the true center of the Milky Way lay roughly 50,000 light-years away in the direction of Sagittarius, far from the Sun's actual location. Shapley's measurement of the galaxy was too large. He miscalibrated his distance scale, partly because he did not account for the dimming effect of interstellar dust on the apparent brightness of his distance indicators. But the fundamental conclusion was right. The Sun was not at the center of the Milky Way. It was a peripheral object, far from the galactic core, occupying an unremarkable position somewhere in the disk. This was a profound displacement of human significance from the center of things, echoing the Copernican displacement from the center of the solar system centuries earlier. The recognition that the Milky Way was a spiral galaxy came gradually through the 1920s and 30s as better data accumulated on the distribution of hot blue stars and the patterns of interstellar gas. By the time W. Morgan built his nail and cotton model in 1951, the spiral interpretation was plausible but unconfirmed. What Morgan did with his wooden board was provide the first real observational evidence that the immediate neighborhood of the Sun showed the elongated banding pattern expected from a spiral arm. He was not identifying the full arm. He was tracing its local segment, but it was enough to demonstrate that spiral structure was real and that our Sun sat within it. The radio surveys that followed in the 1950s and 60s used the 21-centimeter emission from neutral hydrogen to map the arm structure of the entire Milky Way, not just the local region. This was the first time astronomers could see through the dust and trace the large-scale distribution of gas across the galactic disk. What they found was broadly consistent with a spiral pattern, though the details were difficult to interpret because measuring precise distances to hydrogen gas clouds from their radio emission alone is complicated by the ambiguity introduced by the galaxy's rotation. A given radial velocity in the radio spectrum could correspond to two different distances along the line of sight, and disentangling these ambiguities required additional data and assumptions. The Massa Parallax program that began producing results in the early 2000s was the most significant improvement in galactic mapping since the radio surveys of the 1950s. Very long baseline radio interferometry is a technique that combines signals from radio telescopes spread across thousands of kilometers to achieve angular resolutions vastly sharper than any single dish could provide. By combining signals from antennas in the United States, Europe, and other continents, astronomers can measure angular positions with precisions of a few hundred microarcseconds. At the distances relevant to the Orion Arm, this precision translates into distance uncertainties of only a few %, far better than any previous method. The key targets for this technique are masers, which stands for microwave amplification by stimulated emission of radiation. In the interstellar medium, certain molecular species, particularly water and methanol, can be excited to high-energy states by the radiation from nearby young stars and then undergo stimulated emission, producing intense narrow beams of microwave radiation at specific frequencies. These astrophysical masers are extraordinarily bright and compact, making them ideal targets for high-precision position measurements. By tracking a mass's position over the course of a year as the Earth orbits the Sun, astronomers can measure the tiny parallax shift in its apparent position against background quasars and calculate its distance with precision. The Bar and Spiral Structure Legacy Survey, abbreviated BESSEL, is an ongoing program at the National Radio Astronomy Observatory's Very Long Baseline Array that has measured parallax distances to hundreds of maser sources throughout the Milky Way over the past 2 decades. The results from BESSEL have revolutionized our understanding of both the galaxy's overall spiral structure and the Orion Arm's place within it. The survey has established distances to star-forming regions in the Orion Arm, the Sagittarius Arm, the Perseus Arm, and the Scutum Centaurus Arm, providing the most comprehensive and accurate 3-dimensional map of the galaxy's spiral structure ever assembled. The picture that emerges from BESSEL is of a Milky Way with more complex spiral structure than the simple 4-arm model that dominated textbooks for decades. The arms are not cleanly separated and uniformly spaced. They show kinks, branching features, and gaps. The Orion Arm itself appears in the BESSEL data as a coherent structure with a well-defined pitch angle, meaning the angle at which the arm crosses circles centered on the galactic center, consistent with a genuine spiral arm rather than a mere spur. The pitch angle of the Orion Arm, measured from Massa Parallax data, is approximately 12 degrees, comparable to the pitch angles of the Sagittarius and Perseus arms. This consistency is one of the strongest arguments that the Orion Arm should be classified alongside the galaxy's other major spiral features rather than relegated to minor. Status. The pitch angle matters because it determines how tightly the arm winds around the galaxy. A spiral arm with a small pitch angle wraps tightly and appears nearly circular when viewed from above. An arm with a larger pitch angle is more open, less tightly wound, and appears as a more elongated feature in a top-down view. The Milky Way's arms, with pitch angles in the range of 10 to 15 degrees, are moderately open spirals, similar in appearance to well-known spiral galaxies that have been photographed in detail from outside. The comparison with other galaxies is instructive. When astronomers photograph a face-on spiral galaxy, they can see its spiral structure directly. The arms appear as bright blue-white ribbons of massive young stars embedded in diffuse older stellar populations. The brightest knots in those ribbons are star-forming regions analogous to our Cygnus X complex, or the Orion Nebula region. The dark lanes threading between the bright stellar regions are dust clouds, analogous to the molecular clouds that fill the Orion Arm's interior. The entire arm, seen from outside, is a feature of obvious and striking structure. What we see in the night sky when we look through the Orion Arm is the inside view of exactly that kind of feature. We cannot see the arm's shape because we are embedded in it. We see individual objects within it, the stars and nebulae and clusters, without being able to perceive the larger pattern they trace. It is as though you were standing in the middle of a painting the size of a city and trying to understand the image from your position inside it. You can see the brushstrokes immediately around you in exquisite detail. You cannot see the overall composition. You need to step back, which is precisely what our position inside the arm prevents us from doing. This limitation is not permanent in principle. As the Gaia mission and its successors continue to improve our three-dimensional maps of stellar positions, distances, and motions, the picture of the arm's structure becomes progressively clearer. The Gaia mission's final data release, which will eventually incorporate the full dataset from its 11-year observation period, is expected to provide distance measurements precise enough to trace the arm's structure out to several thousand light-years from the Sun with confidence. Beyond that distance, dedicated radio surveys using massive parallaxes will extend the map to the arm's more distant reaches. The next generation of radio interferometry facilities, including the planned next-generation Very Large Array and proposed additions to global Very Long Baseline Arrays, will eventually measure parallax distances to mesas throughout the entire Milky Way disk, providing a three-dimensional map of the galaxy's spiral structure at a level of detail that current technology cannot achieve. When that data arrives, the debate about the Orion Arm's true classification, its exact length, and its precise relationship to the adjacent major arms may finally be resolved with enough precision to settle the outstanding questions. But even without that final resolution, the current picture is already striking enough. The Orion Arm is large, it is active, it is structurally complex, and it is the galactic neighborhood, the immediate cosmic environment, the place that shaped our sun and our planet, and the conditions that made life on Earth possible. Understanding it is not merely an exercise in astronomical curiosity. It is part of understanding where we come from and what the environment was like that allowed us to come from it. Consider the arm's role in the Sun's history more concretely. The Sun formed roughly 4.5 billion years ago from a collapsing molecular cloud. That cloud existed within the Orion Arm, or perhaps within an ancestral arm structure that later evolved into what we now call the Orion Arm. The cloud collapsed because something triggered its collapse, possibly the passage of a nearby density wave, possibly the shock wave from a nearby supernova. The material in that cloud came from previous generations of stars that had lived and died in the arm, enriching the interstellar medium with the carbon, oxygen, nitrogen, silicon, iron, and other heavy elements that make up the non-hydrogen composition of our solar system. Everything in the solar system that is not hydrogen or helium. Every atom of every rock, every molecule of every ocean, every element in every living cell was synthesized in stars that burned and died inside the Orion Arm or its predecessor structure over the preceding billions of years. The arm is not merely the neighborhood the Sun currently occupies. It is the ecosystem that produced the raw materials from which the Sun and everything around it was built. We are the arm's products in a very literal chemical sense. The timeline of the arm's influence on Earth extends beyond formation. As the solar system has orbited the galactic center over 4.5 billion years, it has passed through the Orion Arm's denser regions multiple times. Each passage changed the interstellar environment around the heliosphere. During periods when the Sun was moving through dense molecular cloud regions, the heliosphere, the bubble of solar wind that deflects cosmic rays and interstellar particles from the inner solar system, was compressed. More interstellar material penetrated closer to Earth. Cosmic ray flux increased. The chemical composition of the interplanetary medium changed. Some researchers have proposed that these periodic variations in the galactic environment, driven by the Sun's orbital motion through the arm's structure, may have influenced Earth's climate by modulating the cosmic ray flux that reaches Earth's lower atmosphere. Cosmic rays ionize atmospheric molecules and may seed the formation of cloud condensation nuclei, potentially affecting cloud cover and surface temperature. The mechanism is controversial and the magnitude of the effect is debated, but the basic physics of the interaction between the galactic environment and the heliosphere is well established. What is less controversial is that the galactic environment has had direct physical effects on the solar system's small body populations. When the solar system passes through a denser region of the interstellar medium, gravitational perturbations from passing molecular clouds and stellar encounters at closer range than average can disturb the Oort cloud, the vast reservoir of comets that surrounds the solar system in a shell extending to roughly 1 to 2 light years. These disturbances can send comets on plunging trajectories into the inner solar system, increasing the rate of impacts on the terrestrial planets. The statistical connection between the Sun's position in the galactic environment and the impact rate on Earth is another area of active research, with some paleontological studies suggesting correlations between proposed galactic crossing periods and periods of elevated biological turnover in the fossil record. The correlations remain controversial, but they point to a genuine physical pathway through which the Orion Arm's internal structure could have influenced the history of life on Earth. The arm has also been the setting for some of the most significant stellar events in our solar neighborhood over the past 100 million years. The Scorpius-Centaurus OB association, which lies roughly 400 light-years from the Sun and is itself embedded in the Orion Arm, has been the site of an estimated 15 to 20 supernova explosions over the past 15 million years. These explosions are the ones that carved the local bubble. They are the reason our immediate interstellar environment is less dense than the surrounding arm. And they are the reason the Sun currently drifts through a region of relatively thin gas, rather than a denser portion of the arm's molecular material. These nearby supernovae may also have left chemical traces in the solar system itself. Researchers have found elevated concentrations of certain radioactive isotopes, particularly iron-60 and plutonium-244, in samples from the lunar surface and in deep-sea sediments on Earth. These isotopes are produced in supernova explosions and have half-lives short enough that their presence in geological deposits of specific ages suggests direct deposition from nearby stellar explosions. The iron-60 signal in deep-sea ferromanganese crusts shows several peaks corresponding to different time periods, with the largest peak around 2 to 3 million years ago. This timing coincides roughly with the expected passage of the solar system through the outskirts of the remnant bubble created by the young supernova that produced the nearby Geminga pulsar, one of the closest known pulsars to Earth. If this interpretation is correct, a stellar explosion within the Orion Arm delivered measurable quantities of freshly synthesized radioactive material directly to Earth's surface within the last few million years. The sky above the early hominin ancestors who lived through that period may have briefly brightened with a nearby supernova. We do not know whether early humans or pre-human primates observed it. The geological record does not speak to that level of detail. But the iron in those ancient ocean sediments came from inside the Orion Arm and fell to Earth. The arm that contains us is not passive scenery. It is a dynamic environment that has repeatedly interacted with our planetary system, shaped the conditions under which life developed, and left physical traces that modern scientists are still discovering and interpreting. Every new measurement of the arm's structure, every new catalogue of its stellar populations, every new calculation of the solar system's past trajectory through its interior adds to a picture of our galactic home that is stranger and more intimate than the conventional cosmic address would suggest. The relationship between the Sun and the Orion Arm is not like the relationship between a house and the city it sits in, where the city is background and the house is foreground. It is more like the relationship between a fish and the ocean it swims through. The ocean made the fish. The ocean feeds the fish. The ocean's currents carry the fish to different environments. The ocean's chemistry is incorporated into the fish's body. The fish cannot survive outside the ocean. In the same sense, our Sun cannot be fully understood in isolation from the arm that produced it, that continues to supply it with the interstellar environment it moves through, and that has repeatedly shaped conditions in the solar system during the Sun's long orbital history. The Orion Arm, in this light, is not just a geographical fact about where we happen to be located. It is a biological and historical fact about where we came from and how we got here, the conditions that made Earth habitable, the abundance of heavy elements in our solar system, the relative stability of the Sun's environment over billions of years, the periodic disturbances that drove evolutionary change through extinction events and recovery. All of these are connected to the arm's structure and to the Sun's orbit through it. This perspective makes the arm's invisibility to ordinary awareness feel almost ironic. The thing that most profoundly shaped the conditions for our existence is the thing we are least aware of. Not the Sun, which we see every day, not the Earth, which we stand on, not even the broader galaxy, which most people have at least encountered in diagrams. The Orion Arm, the intermediate structure, the layer of galactic architecture that physically connects the solar system to the larger cosmos, is the thing that passes without remark in every description of where we live. When future generations describe humanity's cosmic address, perhaps the arm will have earned its proper place in the sequence. Not Earth solar system, Milky Way, but Earth solar system, Orion Arm, Milky Way. The arm deserves to be named. It deserves to be recognized. It is real in exactly the same sense that the solar system and the galaxy are real. It is measurable in exactly the same sense. It is responsible for our existence in a deep sense that neither the solar system nor the full galaxy alone can claim. The scientists who are mapping the arm right now, the radio astronomers tracking mesoparallaxes, the stellar cartographers processing Gaia data, the molecular cloud surveyors piecing together the arm's gas inventory, are doing something that can reasonably be compared to the great geographical explorations of earlier centuries. They are mapping a territory that is genuinely new to human knowledge, a territory of vast dimensions that was hidden not by its distance, but by our position inside it. The exploration is ongoing. The map is incomplete. The discoveries are still arriving. And the most fundamental fact about the arm, the one that underlies all the numbers and measurements and scientific revisions, remains the one that takes the longest to absorb. The Orion Arm is home, not in the abstract sense that the galaxy is home or the universe is home, but in the specific physical sense that it is the galactic structure immediately surrounding our solar system, the environment we have occupied for the Sun's entire 4.5 billion year history, the cosmic neighborhood that has shaped our world more directly than any structure beyond it. Home is 20,000 light-years long. Home contains billions of suns. Home includes a 9,000 light-year oscillating wave of gas and newborn stars. Home produced the heavy elements in our bones. Home carved the local bubble we drift through. Home has sent radioactive debris raining onto our ocean floors. Home will outlast everything our civilization will ever build. We are inside it right now. And we are only beginning to understand what that means. There is a concept in astronomy called the zone of avoidance. It refers to the region of the sky along the plane of the Milky Way, where dust and gas are so dense that optical telescopes see almost nothing beyond our own arm's immediate vicinity. Galaxies that lie behind the plane of the Milky Way are simply invisible to optical instruments. This zone of avoidance stretches as a dark band across the full sky, marking the edges of the Orion Arm's own obscuring material combined with the deeper dust of the galactic disk. It is a visual reminder of how thoroughly our arm screens us from the broader universe, even as we try to observe outward. Modern radio and infrared telescopes have partially penetrated the zone of avoidance, revealing hidden galaxy clusters and large-scale structures that optical astronomers had simply never seen. The Great Attractor, the mysterious overdensity of mass toward which the Milky Way and millions of surrounding galaxies are gravitationally flowing, sits behind the galactic plane in the zone of avoidance. For decades, astronomers knew something was pulling matter in our direction, but could not see what it was because the Orion Arm's dust blocked the view. It took decades of radio and X-ray observations to identify the culprit as a vast supercluster of galaxies, the Norma cluster region, sitting roughly 250 million light-years away. The arm that we live inside was hiding a structure weighing 10,000 times as much as the Milky Way. The Orion Arm does not merely shape our view of the local galaxy. It shapes our view of the entire observable universe by determining which directions are clear and which are obscured. Cosmological surveys of the large-scale structure of the universe have to account for the zone of avoidance when constructing their three-dimensional maps of galaxy distributions. The missing data along the galactic plane introduces systematic uncertainties into measurements of cosmic flows and matter distributions that cosmologists work carefully to correct for. Our position inside the arm has observational, consequences that extend to the larger scales of the cosmos. The Arm's dust is also the reason that many historical debates about the structure of the galaxy took so long to resolve. The Milky Way's central bar, the elongated, dense structure connecting the two ends of the galaxy's primary spiral arms, was not confirmed until the 1980s and only properly characterized in the 2000s, partly because the bar lies behind the most opaque dust regions of the galactic plane. The spiral arms on the far side of the galaxy remain the least well-characterized parts of the Milky Way's structure, again, because the dust in the arm we inhabit and in the disk between us and the far side blocks the view. In a very real sense, our embedded position inside the Orion Arm has set the pace of human knowledge about the Milky Way. We understand our arm better than any other because it is the one we can see from inside. Everything else requires inference, radio penetration of the dust, and increasingly sophisticated measurement techniques to reveal. There is a beautiful paradox here. The structure that makes itself hardest to see, the arm we live inside, is also the structure we understand best. We have resolved its nearby stars individually. We have measured the distances to hundreds of its stellar associations and clusters. We have mapped its molecular cloud complexes in 3 dimensions. We have traced its internal wave structure. We have determined the Sun's precise location within it. By contrast, the major arms on the far side of the galaxy are known primarily from statistical distributions of hydrogen gas and from indirect measurements of masses in their densest star-forming regions. The Orion Arm is simultaneously the most and least known part of the Milky Way, most known in terms of individual resolved objects and precise 3-dimensional structure, least known in terms of its shape as a whole, because to understand the shape of the whole, you need a vantage point outside it that we do not have. The mathematics of the arm's dynamics are worth lingering on for a moment, because they reveal something important about why spiral arms exist at all and why the Orion Arm is where it is. The spiral arms of the Milky Way are not like the spokes of a wheel, rigidly attached to the galaxy's center and rotating with it. If they were, they would wind up over time, tightening into a dense ring rather than maintaining their open spiral pattern. This is sometimes called the winding problem of spiral galaxies, and it was one of the central puzzles of extragalactic astronomy in the mid-20th century. The solution, developed by C.C. Lin and Frank Hsu in 1964, is the density wave theory. In this picture, the spiral arms are not physical objects that rotate with the galaxy's stars. They are density waves, patterns of enhanced gravitational potential that rotate around the galaxy at a different speed than the stars themselves. Stars and gas move through the arms the way water molecules move through an ocean wave. The wave propagates, but the individual water molecules do not travel with it over long distances. Similarly, the arm pattern rotates around the galaxy at a specific angular velocity called the pattern's speed, while individual stars and clouds orbit the galaxy at their own speeds, determined by the galaxy's mass distribution. At most positions in the galactic disk, stars move at a different speed than the pattern does. Only at a specific radius from the galactic center, called the corrotation radius, do stars orbit at the same speed as the pattern, and thus stay in roughly the same position relative to the arm for extended periods. Our Sun sits at a galactic radius where its orbital speed and the arm pattern speed are somewhat different, which means the Sun does not stay permanently associated with any particular spiral arm. Over the Sun's orbital history, it has passed in and out of arm-enhanced density regions multiple times. The density wave picture explains why the Orion Arm is denser than the interarm regions, even though the specific stars within it are constantly changing. The higher density is a feature of the wave pattern itself, not of any permanent collection of specific stars. As gas and stars enter the region of enhanced gravitational potential, they are compressed. The compressed gas cools, forms molecular clouds, and eventually collapses to form new stars. The new bright blue massive stars light up the arm from inside, making it visible in photographs of other spiral galaxies. By the time those massive stars die a few million years later, the arm pattern has moved on, and the dying stars are no longer within the densest part of the arm. The arm constantly refreshes its population of bright young stars as new batches of gas are compressed by the passing density wave. This process means that the Orion Arm's identity as a star-forming region is self-renewing. The specific stars within the arm today are different from the stars that occupied the same arm location 10 million years ago or 100 million years ago. The arm is not a stable collection of stars. It is a process, a continuously operating machine for compressing gas and igniting new suns, maintained by the gravitational dynamics of the spiral density wave. The Radcliffe wave is probably a feature of this larger dynamic system, a large-scale density perturbation within the arm that is itself maintained and organized by the arm's gravitational environment. The Sun currently sits near the corrotation radius of the Milky Way, which means it orbits the galaxy at nearly the same speed as the spiral pattern. This has an interesting consequence. Stars at other galactic radii move in and out of arm regions repeatedly over cosmic time. Stars near corrotation spend relatively long periods in a consistent relationship with the arm structure. Some researchers have suggested that our position near corrotation may have contributed to the relative stability of the Sun's galactic environment over the time period relevant to the development of life on Earth, a star that repeatedly plunged through the densest inner parts of major spiral arms would experience more frequent close encounters with massive star-forming regions, more nearby supernova, and more gravitational disturbances to its planetary system. The Sun's near corrotation position may have partially shielded Earth from the most violent arm-crossing events, contributing to the relatively stable billions of years that complex life required to evolve. This is speculative, and the contribution of this effect relative to other factors in Earth's habitability is uncertain. But the physics is real, and the question is being actively investigated. The larger context of the Orion Arm within the Milky Way also includes the arm's relationship to the galaxy's dark matter halo. The Milky Way is embedded in an enormous halo of dark matter, extending to perhaps 300,000 light-years from the galactic center, several times larger than the visible disk. This dark matter halo provides most of the Milky Way's total gravitational mass, and its distribution determines the rotation curve of the galaxy, the relationship between orbital speed and distance from the center that astronomers use to infer the presence of dark matter. The Orion Arm sits well within the dark matter halo, as does every part of the Milky Way's disk. The arm's dynamics, the speed at which stars orbit within it, the gravitational forces that shape its molecular clouds, the rate at which the spiral density wave propagates through it, all of these are influenced by the dark matter halo's gravitational field. In a sense, every star being born in the Cygnus X complex right now is being born under the gravitational influence of a vast invisible structure that extends hundreds of thousands of light-years beyond the arm's visible boundaries. The arm is a visible feature of an invisible gravitational system whose full extent dwarfs even the galactic disk. Beyond dark matter, the Milky Way is also embedded in a diffuse hot gas corona, a roughly spherical distribution of hot plasma extending to similar distances as the dark matter halo. This gas was partially blown out of the galactic disk by supernova explosions and stellar winds over the galaxy's lifetime, and partially accreted from the intergalactic medium. The corona interacts with the disk at its boundaries, with gas from the corona raining back into the disk in a galactic fountain driven by the pressure difference between the hot halo and the cooler disk material. Some of this returning gas flows through the Orion Arm, becoming part of the interstellar medium that will eventually be incorporated into new molecular clouds and new stars. The Arm's gas budget is not a closed system. It exchanges material with the galactic halo on timescales of hundreds of millions of years, continuously cycling elements between the cold, dense arm environment and the hot, diffuse halo. These large-scale connections between the arm and the broader galactic environment illustrate why understanding the Orion Arm's structure and dynamics matters beyond the immediate goal of knowing where we are. The arm is not a standalone object. It is a node in a larger network of gas flows, gravitational dynamics, chemical evolution, and stellar population history that constitutes the Milky Way as a living system. Every measurement of a massive distance in the arm, every three-dimensional map of its dust distribution, every new measurement of a star-forming region's physical properties, contributes to the understanding of how the galaxy as a whole processes gas into stars and returns the products of stellar nucleosynthesis to the interstellar medium. For the next generation, the Milky Way has been making stars for over 12 billion years. The Orion Arm, or whatever precursor spiral structure occupied this region of the disk in earlier epochs, has been part of that process throughout the galaxy's history. The heavy elements that enabled the formation of rocky planets like Earth were built up over billions of years of stellar cycling in structures like the Orion Arm. Each generation of massive stars, burning through their hydrogen and helium in a few million years, synthesized heavier elements in their cores, spread them through the arm in supernova explosions, and enriched the interstellar medium that the next generation of stars would form from. The arm is a chemical processing factory, as much as it is a gravitational structure, continuously increasing the heavy element content of the gas from which new stars and planets are made. This chemical enrichment story is part of why life on Earth was possible at all. The early Milky Way was predominantly hydrogen and helium. Like all galaxies shortly after the Big Bang, the carbon, oxygen, nitrogen, phosphorus, sulfur, and other biologically essential elements did not exist in significant quantities in the universe's first few billion years. They were built up in stars over cosmic time, with each stellar generation contributing its synthesized elements back to the interstellar medium through winds and explosions. The molecular cloud that formed our solar system roughly 4.5 billion years ago was already heavily enriched with these elements after more than 9 billion years of stellar cycling in the galactic disk. The arm that contained that cloud had been processing gas into stars and returning enriched material to the interstellar medium for the entire preceding history of the Milky Way. We are the downstream products of that process. The carbon in our DNA, the oxygen in our atmosphere, the silicon in our rocks, all of it was manufactured in stars that burned and died inside the Orion Arm, or its predecessors over billions of years. The arm is not background. The arm is biography. It is the story of how the elements that compose us were made and assembled and eventually incorporated into a planetary system complex, enough to produce minds that would eventually ask where they came from. The answer to that question runs through the Orion Arm. Not through the Milky Way in the abstract, not through the universe in the general, but through this specific 20,000 light-year spiral feature, this dense, gas-threaded, wave-bearing, star-forming environment that has been doing its work for billions of years in a relatively quiet corner of a relatively ordinary galaxy. The arm is local. The arm is specific. The arm is ours, and it is so much larger, so much older, so much more complex than the label on any astronomy diagram has ever suggested that understanding its true scale is itself a kind of discovery. We are inside the Orion Arm right now. We have always been inside it. Every civilization that has ever looked up at the night sky has done so from deep within its interior. Every telescope ever built has peered outward through its gas and dust. Every spacecraft ever launched has traveled through its local bubble. Every question humanity has ever asked about the cosmos has been asked from a position embedded inside this specific galactic structure. And the arm, vast and indifferent and alive with the slow fire of stellar birth and death, has been there the whole time, waiting, in the way that structures without consciousness can wait, to be understood. One of the most counterintuitive aspects of living inside a spiral arm is that the arm is simultaneously denser than its surroundings and mostly empty space. The interstellar medium within a spiral arm has an average density perhaps 3 to 5 times higher than the medium between arms. But even this enhanced density is extraordinarily thin by any standard relatable to human experience. The average density of gas in the interarm regions of the Milky Way is roughly 1 hydrogen atom per 10 cubic centimeters. Within the spiral arm, this rises to perhaps a few hydrogen atoms per cubic centimeter on average. The densest molecular clouds within the arm, where star formation actually occurs, reach densities of tens of thousands to hundreds of thousands of molecules per cubic centimeter. This sounds impressive until you compare it to the air you are breathing right now, which contains roughly 27 million trillion molecules per cubic centimeter. The densest star-forming cloud in the Orion Arm is, by terrestrial standards, a vacuum of unimaginable thinness, and yet this thin material, spread across 3,500 light-years of width and 20,000 light-years of length, adds up to an enormous total mass. Spiral arms are massive structures. The Orion Arm alone likely contains enough gas to form hundreds of millions of stars at current densities, and much of that gas is continuously cycling between diffuse atomic form, denser molecular cloud form, and the stellar form it achieves during star formation events. The arm has been cycling this gas for billions of years, steadily building up the heavy element content of successive stellar generations. The arm's dust grains deserve particular attention because they are so consequential for everything. Astronomers have tried to learn about the Milky Way. These grains, typically a fraction of a micrometer in diameter, composed mostly of silicates and carbon compounds, are assembled in the outer atmospheres of evolved stars and then ejected into the interstellar medium through stellar winds and supernova shockwaves. Once in the interstellar medium, they accumulate in the dense molecular cloud regions, where the grain surfaces serve as catalysts for chemical reactions between gas phase molecules. Molecular hydrogen, the most common molecule in the interstellar medium, cannot form efficiently in the gas phase. It forms on dust grain surfaces, where hydrogen atoms can stick, diffuse across the surface, and combine before returning to the gas phase. Without dust grains, there would be far less molecular hydrogen. Without molecular hydrogen, there would be far fewer molecular clouds. Without molecular clouds, there would be far less star formation. The dust in the Orion Arm is not merely an inconvenience for astronomers trying to observe through it. It is a fundamental component of the Arm's ability to form new stars. The composition of interstellar dust in the Orion Arm has been extensively studied using spectroscopic observations at infrared and ultraviolet wavelengths. The extinction curve, meaning how the dust absorbs different wavelengths of light, reveals information about grain sizes and compositions. The Arm's dust shows a broadly typical composition for the Milky Way disk, with a mixture of silicate grains and carbonaceous grains in varying proportions depending on the local environment. In dense molecular clouds, additional molecular ice mantles form on the grain surfaces, adding layers of frozen water, carbon monoxide, carbon dioxide, methanol, and more complex organic molecules. These ice mantles are the seeds of prebiotic chemistry, the molecular building blocks that eventually become incorporated into planetary systems and potentially into the chemistry of life. Complex organic molecules have been detected throughout the interstellar medium of the Orion Arm using radiospectroscopy. Molecules including glycolaldehyde, a simple sugar precursor, amino acid precursors, and dozens of other carbon-bearing species have been found in molecular clouds throughout the Arm. The organic chemistry of the Arm is rich and varied, driven by the radiation environments of nearby stars, the catalytic surfaces of dust grains, and the thermal gradients between dense cloud interiors and their exposed edges. The Arm is not a chemically inert corridor of gas and stars. It is a vast low-temperature laboratory in which complex organic chemistry operates continuously at scales of hundreds of light years. The molecules that eventually seeded early Earth's chemistry through cometary delivery and interplanetary dust may have had their origins in just this kind of chemistry, occurring in molecular clouds that existed within the Orion Arm hundreds of millions of years before the Sun formed. The relationship between the Arm's chemistry and the origins of life is one of the most tantalizing areas of ongoing research at the intersection of astrochemistry, planetary science, and astrobiology. The growing catalogue of complex molecules detected in molecular clouds throughout the Arm suggests that the chemical precursors to life are not rare products of special conditions. They are standard outputs of the kind of chemistry that operates throughout spiral arm environments. This does not prove that life is common in the universe. Chemistry is necessary but not sufficient for life, but it does suggest that the chemical groundwork for life is laid systematically by the same processes that make spiral arms active star-forming regions. The Arm does not just produce stars, it produces the chemical complexity that makes inhabited planets possible. This perspective situates the question of life in the cosmos within the context of galactic structure in a way that is rarely appreciated. The conditions most favorable for the chemistry of life, the presence of heavy elements, of complex organic molecules, of warm, rocky planets orbiting stable stars in environments neither too radiation blasted nor too chemically impoverished, are most likely to be met within spiral arms. The Arm's elevated density of star formation, its ongoing synthesis of heavy elements, its rich organic chemistry, its moderate radiation environment, all of these factors contribute to the plausibility of living worlds within it. The Orion Arm may not just be where we happen to live. It may be the kind of environment where life is most likely to emerge in any galaxy. The question of whether any other civilization in the Orion Arm has ever looked up from its planet and wondered about the structure of the arm it lives in is one that current science cannot answer. The Arm contains billions of stars. A significant fraction of those stars likely host planetary systems. A smaller fraction of those planetary systems likely include rocky planets in habitable zone orbits. Whether any of those planets host life and whether any of that life has reached a technological phase is unknown. The distances separating any two potentially inhabited systems within the Arm are measured in hundreds to thousands of light years. Communication across such distances, even at the speed of light, takes centuries to millennia. The Arm's scale makes the prospect of meaningful contact between civilizations within it profoundly difficult, even in principle. The neighbors we might share the arm with are separated from us, not by the kind of distances that exploration could eventually bridge, but by the kind of distances that make even radio contact a matter of geological patience. This is the loneliness embedded in the arm's scale, not the abstract loneliness of an empty universe, but the specific practical loneliness of a structure so large that even its nearest residents are inaccessibly far apart. Whatever else might exist within the Orion Arm, it exists beyond our reach, beyond our sight, beyond our ability to signal or to receive a signal within any time frame that connects to human civilization's past or foreseeable future. The arm contains us, and it contains whatever else is in it. And the two are separated by the fundamental fact that light itself needs centuries to cross the distances between them. This is the final implication of the arm's scale that takes the longest to sit with. We are not alone in the arm, in the sense of being the only matter or the only stars or the only planetary systems within it. The arm contains billions of stars and untold numbers of worlds. But we are alone in the arm in the sense that matters most practically. We cannot reach any of them. We cannot hear any of them. We cannot see any of them directly. And we cannot know whether any of them harbor anything that would recognize us as neighbors, rather than as the faint blue pixel that Earth represents from across the arm's distances. The arm is populous and the arm is silent, and the silence is not evidence of emptiness. It is the silence of scale, a silence that would exist even if every star in the arm had a civilization around it, simply because the distances between them make contact a project measured not in years or decades, but in geological epochs. We have been asking questions about the Orion Arm for less than a century. We have had the technology to answer some of those questions for less than a generation. The map is incomplete. The questions are numerous. The answers are coming slowly through the patient accumulation of precise measurements and the development of new observational capabilities. What we already know is enough to fundamentally revise the picture of where we are. What we will eventually know will revise it further. The arm is 20,000 light-years long. It contains billions of stars. It hosts a 9,000 light-year oscillating wave of gas and newborn suns. It produced the heavy elements in our cells. It carved the local bubble we drift through. It has repeatedly altered conditions on Earth through its supernovae and its gas clouds. It is the immediate galactic environment, the layer of cosmic structure between the solar system and the full Milky Way, the thing that has been surrounding us for the entire history of life on this planet. We are inside it right now, as we have always been, and we are only beginning, with the tools of modern astronomy and the patience of careful science, to understand what it means to be home in a place this large. The Gaia mission's contribution to understanding the Orion Arm cannot be overstated. Before Gaia, stellar distances beyond a few hundred light-years relied on indirect methods that carried substantial uncertainties. The nearest stars had been measured by ground-based parallax programs for over a century, but these programs were limited by atmospheric blurring and the finite precision of ground-based measurements. The Hipparcos satellite, Gaia's predecessor, measured precise parallaxes for about 120,000 stars out to roughly a few hundred light-years with reasonable accuracy. Gaia extended this to nearly 2 billion sources out to several thousand light-years, with precision improvements of roughly 100 times over Hipparcos for many source types. The practical effect of this improvement is profound. A distance measurement with 10% uncertainty for a star at 2,000 light-years places that star somewhere between 1,800 and 2,200 light-years away, a range of 400 light-years. A measurement with 1% uncertainty places it between 1,980 and 2020 light-years, a range of 40 light-years. Multiplied across millions of sources, this improvement in precision transforms a blurry statistical picture of the arm's structure into a sharp three-dimensional map. Objects that previously appeared to be in roughly the same general region of the arm can now be placed at precisely determined distances relative to each other, revealing whether they are genuinely associated or merely appear near each other along the line of sight. It was exactly this precision that allowed the Radcliffe wave to be identified. The individual star-forming regions that constitute the wave had been known for decades. The Orion Nebula, Taurus, Perseus, all of them were catalogued and studied. But without precise three-dimensional distance information, there was no way to know whether these regions lay at similar heights, above or below the galactic midplane. They appeared as roughly two-dimensional features on the sky, with uncertain distances that blurred their three-dimensional arrangement. Gaia's precise parallaxes allowed researchers to place each region at its correct distance and height within the galactic disk, revealing for the first time that these independently studied features were vertically arranged in a coherent sinusoidal pattern. The wave was always there. The technology to see it had not yet been invented until Gaia flew. This pattern of discovery, structures that exist but cannot be detected until the right measurement technique arrives, is likely to continue as new observational capabilities come online. The Square Kilometre Array, a radio telescope network under construction in South Africa and Australia that will eventually have a collecting area of approximately 1 square kilometre, will detect hydrogen and molecular masses at distances, and with sensitivities far beyond current capabilities. When it reaches full operation, it will extend precise Meister parallax measurements to the far side of the Milky Way for the first time, providing distance data for spiral arm features that current surveys can only detect statistically. The far reaches of the Orion Arm, the portions toward Carina that remain poorly characterized, will become accessible to direct distance measurement for the first time. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will survey the sky in infrared with a wide field of view comparable to Hubble's but covering areas of sky roughly 200 times larger per pointing. Its surveys will penetrate the galactic dust along the plane of the Milky Way to distances far greater than visible light surveys can achieve, revealing the stellar population of the arm's interior in regions currently hidden behind dust curtains. The combination of Roman infrared data with Gaia astrometry will allow three-dimensional dust maps to be extended further from the Sun than currently possible, revealing the arm's structure in volumes of space that remain essentially unmapped. Ground-based next-generation spectroscopic surveys, including those planned for the Vera Rubin Observatory and the Weave spectrograph in the Canary Islands, will measure radial velocities for hundreds of millions of stars across the Milky Way disk, providing the kinematic information needed to complement Gaia's position data. Together, positions plus velocities equals the full three-dimensional picture of where everything is and where it is going. With both in hand for hundreds of millions of stars, the reconstruction of the arm's spiral structure from the inside becomes a genuinely tractable problem, not a measurement, limited by the precision of individual distance estimates. The next decade of astronomical data will transform our understanding of the Orion Arm, from a structure we have begun to recognize to one we have genuinely mapped. The transition from the sketchy outline provided by Morgan's 25 nails in 1951 to the preliminary, three-dimensional structure revealed by Gaia represents roughly 70 years of technological development. The transition from the current preliminary picture to a comprehensive map of the arm's full extent will likely take another 1 to 2 decades of sustained observational effort. When that map is complete, the Orion Arm will be the best characterized spiral arm of any galaxy in the universe, including any distant galaxy photographed from outside, because we will have resolved its individual stars and clouds and structures with a precision that no external view of a distant galaxy can match. That is an extraordinary reversal of the obvious. The arm that seems hardest to study because we are trapped inside it will eventually be better understood than the arms of any galaxy we can photograph from a comfortable external vantage point. The obstacle of being inside the structure is ultimately less limiting than the obstacle of being too far away to resolve individual stars and clouds. Distance blurs everything. Proximity with the right instruments reveals everything. The arm will eventually be known from the inside in a way it could never be known from the outside. This is perhaps the most hopeful note in the story of the Orion Arm. We are not condemned to permanent ignorance by our embedded position. We are temporarily limited by the precision of our measurements. Those limitations are shrinking with every new satellite launched, every new telescope built, every new parallax measurement completed. The arm is coming into focus, the map is being drawn, and the picture that is emerging, even in its current preliminary form, is already extraordinary enough to revise everything most people think they know about where they live in the cosmos. 20,000 light-years of spiral arm, stretching from Cygnus to Carina, holding billions of stars, threading through with a 9,000 light-year oscillating ribbon of gas, hosting the birth and death of suns in a continuous cycle that has been running for billions of years, and inside all of it, near the inner edge, tucked into a 1,000 light-year bubble of relatively thin gas, orbiting an unremarkable yellow star, living on a small rocky planet that the arm does not notice and cannot see. That is where we are. That is home, And now, for the first time in the species' history, we know it.